All right, so we're starting at part one. So with part one, we're going to kind of talk about our properties of exponents really quickly, and then we're going to talk about how to graph and analyze exponential functions. Again, I may go a little fast just because hopefully you catch on. You're like, oh yeah, dust those cobwebs off, and you remember how to do it. All right, so up first, we have our properties of exponents. Sometimes they're called exponent laws, laws of exponents, but basically they're the rules that apply when you are dealing with exponents. So if you look right here, we have our first rule. Our first rule that we have present is our power distribution rule. When you have a power outside of parentheses, it distributes to every factor. Okay. Notice I'm saying factor, not term. It distributes to every factor. So you get an M, you get an M, we all get an M. Yes, do you remember that rule? Okay. When you have a power times a power with parentheses, because there's only one base but two powers, those powers are multiplied. Okay, that's our power, power times power rule. Now, this is our product power rule, power of product, meaning that I have bases are the same, powers are separate. That means I'm adding them together, right? Do you remember that? Okay. Next is our rational power rule. When you have a rational power, this is called a unit fraction. Does anyone remember a unit fraction from elementary? Okay. A unit fraction, it won't let me write. I didn't want to write anyway. That okay, I do want to write. Please be my friend. There it is. All right, a unit fraction means that your numerator is a 1. Okay, so this is a unit fraction. And it's a unit fraction because the numerator is a 1. When you have a power of a unit fraction, that just means that you're taking the root of whatever the denominator is. Meaning, if I had 4 to the 1/2, I'm just asking you what is the square root of 4, which is 2. Okay. So when you have a unit fraction as a power, you're just taking the root. All right. When you have a negative exponent, that means that the factor is in the wrong place. So if I have a negative exponent and my factor is in the numerator, that means it actually belongs in the denominator. Vice versa, if I have a negative exponent in the denominator, that means it belongs in the numerator. It just means that it needs to be somewhere else. It's unhappy with its current location. So you move it to make it happy. Okay. All right. Next is distribution over quotient, which just means that you're going to distribute to the numerator and to the denominator factors. All right. All these sound familiar? Okay. Next is just putting in the calculator. So the next three are just purely calculator practice. Are you comfortable plugging in and evaluating from a calculator? I would like to believe that we all are very comfortable doing it. I'm going to model it really fast. I'm not even going to write the solutions down. I'm just going to model them in the handy dandy calculator. So I'm going to pull up my Desmos. I'm going to hit refresh and clear everything away. So if you're on Desmos and you're typing in a exponent, you can either click the little keyboard or you can press Shift 6. By pressing Shift 6, it automatically turns it into a power. So now I have 2 and 3/10. There's my answer. Bless you, bless you, bless you. Okay. So again, without having to use the keyboard, I press Shift 6. It turns it into a power. Okay. Did you notice what I typed? Once there, again, if you don't want to have to use the keyboard to get a square root, you type SQRT and it will automatically produce a square root for you. Okay. Once you're there, you then can put in whatever you need. And wham, bam, thank you, ma'am. You have your answer. Okay. The last feature we're going to go over is just making sure with your negative. When you have a negative power, I strongly encourage you to use parentheses to ensure that it doesn't get moved, the number doesn't get displaced. So when I type it in, notice that I'm using parentheses to guarantee that that negative stays and is being applied to that number. All right. Questions about inputting exponentials into the calculator. I was going to copy them, but I don't even feel like writing them down. Yes. Yes. He started math early. His parents put him in it early. Yeah. All right. Are we good? Comfortable? Yeah. Okay. I'm going to move on from calculator. Okay. So moving on from calculator, we can input in the calculator. Yay, we're geniuses. All right. Up next is the characteristics of our exponential function. Okay. When you have the exponential function, remember that your domain is all real numbers, meaning that your domain is from negative infinity to, that's really ugly infinities. I couldn't accept them. They didn't get much better, but you see where I'm going. All right, the range of your exponential, your range depends on your um, horizontal translation, right? But initially starting off, your range is going to be all positive real numbers, meaning that we go from 0 to infinity. Notice that 0 is not bracket because it's not included. It is an asymptote there. All right. For your exponential function, you're only going to have a y-intercept, and that's because you can't cross the x-axis. So all you have is a y-intercept. When you're reading an exponential function, if your base is greater than 1, then you're going to have a growth. So when we have a growth, these are the rules that we follow for growth. Okay. It's increasing function, continuous, and it is concaved up. Now, if your b is between 0 and 1, because your b can't be negative, it is a decreasing function. It's continuous, and it still is concaved up, and that is what we describe as a decay. The parent function is going to always approach but never cross the x-axis, and that's because the x-axis is a horizontal asymptote. So we have a horizontal horizontal at y equals 0. And it is a one-to-one function, meaning that it has an inverse. We'll dive deeper, but the inverse of an exponential is a log function. Okay. So what can you conclude about log functions? Here we go. We're going to graph and compare f of x equals 2 to the x and g of x equals 1/2 x. And we're going to look at them in Desmos and talk about what do you notice? What do they have in common? What do you see as different between the two functions? So we're going to go back to our handy dandy Desmos. Don't need you anymore. Don't need you anymore. And I'm going to graph. So the first one I'm graphing is 2 to the x. Then I'm going to graph Okay, so here are two function models so that I can match the window in your notes. Come over here, and we only go up to, looks like 6. 6, and then we're from -3, huh? -3 to -7 to 17. So this is what is on yours, right? For you to draw your little sketchy sketch out. As you're drawing your sketch, there are key points that you can identify. Main one is that they both share the y-intercept at 0, 1. That's because anything to the 0 power equals what? 1. Anything to the 0 power is going to be 1. Okay? So let's first look at the purple. I'm going to hide the black for a second. So looking at the purple function, you can see that this is just a model showing us when you are putting 2 to a power, right? 2 to the 1, 2 to the 3, 2 to the 4. Okay? I'm going to pull up the table so you can see said values. The reason why I like pulling up the table is because it'll automatically mark those values on the graph for me. Okay, so all I did here was 2 to the negative 2, which is a quarter, right? And then 2 to the negative 1, which is 1/2. 2 to the 0, 2 to the 1, 2 to the 2. Okay, so these are steadily increasing. All right, we're going to turn off purple. I want the points to stay, and we're going to turn on black. Turning on black. Same thing, but this time it's the inverse of it. Because remember when we said when you have a negative power, it's going to take something that's in the numerator and move it to the denominator. So when I had 1/2 to the negative 2, it actually became 1/2 mid 2 to the positive 2, which is why it's the 4. So its values are same numbers, just in opposites, right? They are reflected over the y-axis. Do we see that reflection? So it's asking you to describe, what do you notice between the two? Well, the conclusion is we know that there's a reflection. So let's talk about how that works and what does that mean mathematically. Okay. So do you guys remember our transformation rules? If I have a negative x, it causes me to reflect over the y-axis, right? Negative y, we reflect over the x-axis. So y equals 1/2 to the x is equivalent to 2 to the negative x. That's why you have that y-axis reflection. Reflection. Okay. And the reason being that you have that reflection is if I have 1/2, I can turn this into a non-fraction by making this 2 to the negative 1. And there's already an x there, right? And what happens when you have a power times a power? They are multiplied and are combined. So I take the fraction, I take the denominator, make it to a negative power, and now I'm just using my exponent rules. So essentially they are the exact same thing, which is why that reflection happens. Okay, so the last part of part 1 is just tying back to all of our transformation rules. So when you flip over, you'll see all of our transformation rules and how can they toggle back and forth in terms of exponentials. So if you look up here, we have our vertical translation. Your vertical translation is when you're adding or subtracting, correct? So when I add or subtract to the outside, this is what it looks like. Your vertical translation, that's going to affect your horizontal asymptotes. Okay? Because normally our horizontal asymptote is at 0, right? But if I start shuffling up and down on that y-axis, what's going to happen to my horizontal asymptote? It has to move also, right? It's not going to remain at 0. Okay? Your horizontal translation is when you're near x. Remember, x's are liars, right? So if it looks like it's a minus, I'm actually going to the right. If it looks like a plus, I'm actually going to the left. Essentially, all you're doing here is moving your y-intercept. You're taking your y-intercept and shuffling it, right? That one point is what's moving because everything else is going to follow your y-intercept. All right, our dilations. So remember we started calling them dilations in Algebra 2. Your vertical dilation, well, stretch and compress. All it's saying is how are you growing on the y-axis and or getting wider on the y-axis. That's where we're stretching. Your vertical dilation does not have any impact on your horizontal asymptote. Okay? Your horizontal is the opposite. So your horizontal is going to be the opposite. It looks like you're multiplying, but you're actually dividing. You're multiplying by the reciprocal of whatever that A factor is. So this set, I have 2 to the 1/4 x. It is not actually a compression or a shrink. It is a stretch by 4. Your x's lie in every aspect of transformations, okay? And then your reflections over the x is going to be when it's affecting your y's. Over the y's is when it's affecting your x's. So for the test, you need to be able to identify the change in a transformation without a calculator. You will not be able to graph and say this did this. I need to be able to understand what each aspect did on its own. Does that make sense? So you will not be able to graph and compare like in Algebra 2, where we could graph and compare, say, with left, right, up, down, stretch, and compress. You need to be able to say, okay, looking at what I have, this is what took place, okay? So for example, we're going to start off easy here. Looking here, we have g of x equals 3 to the x plus 2. We have our original, which is 3 to the x. So that's our parent function. So we're going to label this as our parent function. Okay. From here, this is going to be our kid. What traits did this kid get, right? So for our parent function, we're going to fill in our initial values. The initial values are just simply 3 to the negative 2, 3 to the negative 1, 3 to the 0, so on and so forth, right? I'm going to write it out so that you can see what I mean. Okay, 3 to the negative 2. Well, what's 3 squared? 3 squared is 9, but because it's negative, that means it's unhappy in the numerator and it belongs in the denominator. 3 to the 1 is 3. It's unhappy in the numerator, so it belongs in the denominator. And then 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. These are my y values, correct? We all agree? Okay, on the other one here. What's happening here? We now have x plus 2. We're shifting to the left. So if I'm shifting to the left, which values are changing? My x's. Are my y's changing? No, your x values are what's changing. Your y's are staying the same. So when I look here, I'm going to draw a line. My y's are going to stay the same. My y's are currently 1/9, 1/3, 1, 3, and 9. But my x's are changing, right? So to each x, I'm doing what? That plus 3 tells us we're going which way? To the left. So it's going to have to be a subtraction. X's are liars. So to each one of our x's, we are subtracting 2. Does that make sense? So negative 2 minus 2 puts us at negative 4. Negative 1 minus 2 puts us at negative 3. 0 minus 2 puts us at, and then 1 minus 2 puts us at, and 2 minus 2 puts us at 0. So these are now my new x's, and my y's are still the same. Does that make sense? Okay. I'm not going to graph it because we have time, but really quick, the last part of part one is that it says to show that I can write this in terms of a times b to the x. And the reason why this goes back to geometry, we kind of dive, not geometry, algebra 2. If I have 3 to the x plus 2, this means that mathematically I have 3 to the x times 3 to the 2. Do y'all remember that? Because if I'm adding my powers, that means they came from me multiplying two factors with the same base, right? So I can transform this to create a new function. Well, what is 3 squared? 9. And I'm left with 9 times 3 to the x. And then this would be our new function. So these are exactly the same. They're just, when I graph them, they're going to look exactly the same. It's just that one, when you read it, is a horizontal translation, and the other would be a vertical dilation. Do you see the difference? Yes. And then we transformed it into a vertical dilation. And that's because of our exponent. Got it? All right, so you should have enough to do part one. Tomorrow we're going to finish and do part two. Does that make sense? So if you're not going to be here tomorrow, here you go.